Of all the units that we encounter in chemistry, the mole is clearly among the most important. We say that it is a unit of quantity, telling us how much of something that there is. The best analogy I can give to that would be the dozen as a quantity. We know that if we have a dozen of something, we have 12 of it. So a dozen atoms is 12 atoms, a dozen eggs, 12 eggs, etc. The mole is one of these quantity units, and it is used to count things which are extremely small and very, very numerous. And so unlike having the number 12, which we use for dozen, a mole is going to represent a much, much larger number. So we say that if we have 1 mole of something, we have 6.02 times 10 to the 23rd of it. That is a huge number. And we call that Avogadro's number. So we use MOLE, mole, as the name of the unit, but for whatever reason, we also tend to abbreviate it by just dropping off the E. So if you see mole or mole, either way, understand them to mean the same thing. Let's go ahead and take a look at some problems to see how this works out. So let's first start off by working with dozens, a unit that you're familiar with. So we would ask ourselves, how many eggs are in 5.5 dozen eggs? I know that you're totally capable of answering that in the usual way, just multiplying 12 by 5.5, but I want you to see how the units work here, because we're going to use them in an extremely similar way for moles. So what we're given here is 5.5 dozen eggs. To get rid of dozen, we use its definition. So 1 dozen of anything is 12 of that thing. So in the denominator, I'm going to put 1 dozen eggs, and then change that to 12 eggs here. So we see how that works. 1 dozen is replaceable by the number 12. And so if we carry out this calculation, we see that we get 66 eggs. Nothing too surprising there. Now let's solve a similar problem for atoms, but using moles instead of dozen. You'll see that the problem works essentially the same way. So we have 5.5, instead of dozen, we have 5.5 moles. And we are going to use the same concept as we used in the previous problem. 1 mole of something, and in this case it's a mole of atoms, is Avogadro's number of that thing. So Avogadro's number is 6.02 times 10 to the 23rd of whatever we're talking about, so atoms in this case. And so mole of atoms cancels, and we're left with some numbers here. So putting this into the calculator, 5.5 times 6.02 times 10 to the 23rd gives me 3.3 times 10 to the 24. Atoms. A very large number, to be sure. So please do note, it works exactly the same way as dozen when we use moles. How many hydrogen atoms are in 1 molecule of water? How many oxygen atoms? Well, if we're talking about a water molecule, we've already drawn the Lewis structure for these. So let's use that as our starting point. And what we can say here is that every one water molecule has, or is equivalent to, and I'll just use a ratio symbol here, one oxygen atom is equivalent to 2 hydrogen atoms. Notice I'm not using H2 or O2 here because we're not talking about the pure element. So these relationships are going to be useful in the next problem that we're going to look at. So one water molecule is equivalent to having one oxygen atom is equivalent to having 2 hydrogen atoms. Okay, so how many hydrogen atoms are in 1 mole of water? How many oxygen atoms? And how many atoms total? Well, in 1 mole of water, let's use that as our starting point here. We know that 1 mole of anything is Avogadro's number of that thing. So that would be 6.02 times 10 to the 23rd. H2O, and what units would we use here? Water comes as molecules, that's its unit. So I'll write molec. Do not write moles because we don't want to confuse those. So this is H2O molecules. So moles of water have canceled. And I'm going to use the information from this previous page that I just used here. An H2O molecule has two hydrogen atoms. So we just put this into the calculator. 1 times 6.02 times 10 to the 23rd times 2 gives me 1.20 times 10 to the 24. If you are wondering about significant digits, I just said 1 here. I didn't give a specific number, so there's no real sig-digs there. All of these are exact numbers, and Avogadro's number as written has 3 significant digits. We can go out further. For example, 6.022 would be Avogadro's number with 4 significant digits. What about how many atoms are in 1 mole of water if we're talking about the hydrogen atoms? Excuse me, let me say that again. Now let's talk about oxygen. How many oxygen atoms are there? Well, we could rewrite the problem the same way. I have a mole of water. Every mole of water has Avogadro's number of water molecules. And we know that every 1 water molecule has how many oxygen atoms in it? Well, there's only 1, so 1 oxygen atom. So this is just 1 times Avogadro's number. Again, a huge number. How many atoms total? Well, the only thing that is in water is hydrogen and oxygen, so we could total this up by adding those 2 numbers. So the total would be 1.20 times 10 to the 24 plus, I'm going to rewrite this so it has the same power of 10. So this would be 0.602 times 10 to the 24. You should convince yourself that 6.602 times 10 to the 24 is the same as 6.02 times 10 to the 23. So then, when I go to add these, I get 1.80 after adjusting to the correct number of sigdigs times 10 to the 24 total atoms. Let's do some more practice with moles here. So let's say we have 18.5 moles of oxygen gas. Oxygen gas is O2. I want to know how many individual molecules I have. In other words, how many O2s do I have? And also how many individual atoms. So it would be worth noting here that for every one O2 molecule, there are 2 atoms, 2 oxygen atoms specifically. So let's first start off here by finding how many individual molecules I have. So I have 18.5 moles of oxygen gas. If I want to get that to numbers of molecules, I simply use Avogadro's number. So in front of mole, I put 1. So for every 1 mole of oxygen, there are 6.02 times 10 to the 23rd of whatever these are. So what units do O2s come in? They are molecules. So putting this in the calculator, 18.5 times Avogadro's number gives me 1.11 times 10 to the 25. If I want to know how many atoms there are, I can convert between oxygen atoms and oxygen molecules just using this relationship. For every 1 oxygen molecule, there are 2 atoms. So it should be simple enough to see that we're just going to have this number times 2, but let's just write out the units for practice. This will help us in many contexts. So here we have the answer to this question, 1.11 times 10 to the 25 oxygen molecules and using the relationship here, every 1 oxygen molecule contains 2 oxygen atoms. So oxygen molecules cancel. And 2 times 1.11 is simply 2.22 times 10 to the 25th oxygen atoms. You want to be sure that you're very comfortable with these kinds of relationships here. So the number of oxygen molecules to atoms, or similarly what I had up here. Every water molecule has 1 oxygen atom and 2 hydrogen atoms and 3 atoms total, correct? An oxygen atom plus 2 hydrogen atoms. Let's do another practice problem here. So let's say we have methane again, and it has 7.35 times 10 to the 25th atoms. How many moles of methane do I have? So this is very important that we keep the terms straight so we know exactly what we're talking about here. So here we're talking about atoms, and here we want moles of methane. Well, in CH4, we know that for every one CH4 molecule, how many atoms are there? Well, there's one carbon atom, and I could write one of these to one carbon. And there's 4 hydrogen atoms, so I could say one of these to 4 hydrogen atoms. Or there's a total of 1 plus 4 or 5 atoms if I'm being indiscriminate about which type of atoms. And the problem here doesn't say anything about whether it's just carbon atoms or hydrogen atoms. It says atoms total. So every one molecule here has 5 atoms in it. Incidentally, we could also put the word moles in front of this. I want you to think about this. If I have one molecule here, that's 5 atoms. If I have 2 CH4 molecules, I would have twice as many atoms. I would have 10. If I had a dozen of these molecules, it would be this times 12, 5 times 12, or 60. So if I wanted to here, I could just say, going along the same logic, if I had 1 mole of CH4, that would be 5 moles of atoms. Okay, so I'm given here 7.35 times 10 to the 25th atoms. Let's use the relationship that we have here. Every 5 atoms would give us 1 CH4 molecule. And finally, I want to get to moles of methane. So we use Avogadro's number again. So how many molecules are there in a mole? There are 6.022, or we'll just say 6.02 times 10 to the 23rd molecules in 1 mole. Of CH4. Notice I got rid of the word molecules here because mole implies that we're talking about whatever unit CH4 comes in. It comes in molecules. Okay. I'm going to simplify things for myself a little bit before I put this into the calculator. I know that 10 to the 25th over 10 to the 23rd would simply be 10 to the 2nd. Because we divide, exponents means the same thing as subtracting the exponent, so 25 minus 23 is 2. And that keeps things a little bit simpler for going into the calculator. Less opportunity to make a mistake. So 7.35 times 10 to the 2 is exactly the same thing as 735. We want to divide that by 5. And divide that by 6.02. And this gives me 24.4. The answer here is 24.4 moles of CH4. And this problem, more than perhaps any of the ones preceding, should make the point as to why we like to work with moles. When you're dealing with molecules or atoms, you have to deal with huge numbers because atoms and molecules are so very, very small. Dealing with moles makes this much more simple and easy to deal with here. And so that's what we've simply done here. Instead of using a big number like this, we can just say I have 24.4 moles of CH4. Now the mole will have many useful aspects about it, but one of the most important when we first start is to see how we are able to derive masses of both individual molecules and moles of substances from them. So earlier in the course, specifically in Chapter 2, we saw that the average mass of an atom is found on the periodic table. For any given box in a periodic table, we know that we're given the atomic number, the symbol, and typically the atomic mass. So the atomic mass of hydrogen is about 1.008 AMU, and that of helium is 4.003 AMU. And remember, AMUs are very small mass units. They're about 10 to the minus 24 grams. These values we can see on the periodic table. So for hydrogen, there's the 1.008, and here's helium, 4.003. So the formula mass would be what we would get if we just simply added up all the atoms in a particular chemical formula. So for example, let's go ahead and take a look at two of these here. Let's say we're looking at carbon dioxide, and let's say we want to look at water. So what we're going to need to do is look at our periodic table and find these various values. Now there's no need to memorize them, but when you've been doing this as long as I have, you'll find that I've memorized these values. So carbon is 12.01, oxygen is simply 16, and hydrogen, as we already saw, was 1.008. And so the value for hydrogen we've already seen is 1.008, carbon 12.01, and oxygen 16.00. On some periodic tables you see more significant digits than this, but we'll just follow a custom of using 4 from the periodic table. So let's calculate these values. So for carbon dioxide, we're just going to use that value for carbon of 12.01 AMU. And there's only one carbon. There are 2 oxygens. So we now want to take care of the oxygen, so that would be plus 2 times 16.00 AMU from the periodic table for oxygen. And when we add that up, that gives you 44.01 AMU. That is the mass of a single carbon dioxide molecule. So just one of these guys here if we want to draw its Lewis structure. And it should make sense from just looking at Lewis structures that the mass of this would have to be the carbon plus the 2 oxygens. For water, we follow a similar process. Hydrogen we saw was 1.008 AMU, so therefore we have 2 times 1.008 plus oxygen we already saw was 16. So we have one of those times 1, so I don't need to put that in. And this would add up to 18.02 AMU. So that is the mass of just single molecules of each of these compounds. However, rather than measuring in AMUs, we have a much more convenient system here. And this is intentionally how the AMUs were set up. They were set up so that instead of just expressing molecules as AMUs in their mass, we can also say that those values from the periodic table can represent grams per mole of that atom. So, for example, 1 mole of calcium has a mass of 40.08 grams. 1 mole of neon has a mass of 20.18 grams. Those are simply the values, 20.018, for example, here from the periodic table, 40.08 for calcium. And since we're usually going to be measuring in grams, it only makes sense that we would like to have some relationship between moles and grams. So we call this effectively the molar mass of the substance. And it is just the mass of 1 mole of whichever substance we happen to be discussing. So we can essentially find the molar mass of any molecule by doing the same process that we just did for carbon dioxide and water. We're simply going to do it with different units. So we already saw here that every 1 mole of carbon contains, carbon dioxide contains 1 mole of carbon, and it contains 2 moles of oxygen atoms. So we just add them up to get the molecular weight of carbon dioxide. As I did just a moment ago, that was going to add up to 44.01, and this time instead of AMU, we'll say grams per mole. So, and again, the mass of a single molecule we just calculated was 44.01 AMU. We just use a different unit. Now, these are also called molecular weights when we're talking about compounds which actually form molecules, but sometimes we use a similar term, formula weight, instead. It's just much easier to use the word molar mass, molar mass, than going through different terminologies, but formula weight, molar mass, molecular weight, they're all going to mean the same thing to us. So let's calculate then the molar mass of glucose. So going back to our notes page here, we've already saw that carbon was 12.01, oxygen 16.0, and hydrogen 1.008. So we use the exact same process that we just used for carbon dioxide and water with just different units. So for glucose here, we first got the part from carbon. So that would be, there are 6 carbons in the formula, so 6 times 12.01, and instead of AMU, I'm just going to say grams per mole. So that's the contribution from carbon. And then from hydrogen, we have 12 times 1.008 grams per mole. And then from the oxygen, we have 6 times 16 grams per mole. And adding these together should give us roughly 180.15 grams per mole, which I leave to you to verify. I'm going to go ahead here at this point and stop the video, and when we come back we will use this relationship between grams and moles to start working with compounds, and then relating that to chemical reactions, which we started the chapter with. Thank you.